Essayer des trucs, ça me du coup, est-ce que vous m'entendez? Est-ce que vous m'entendez sur le Zoom? Non, non. Alors, c'est que c'est encore compliqué dans les. C'est le réel. Alors là, est-ce que vous m'entendez? Oui. Vous m'entendez sur le Zoom? Et est-ce que vous m'entendez sur le YouTube dans les 10 secondes que ça va mettre à passer sur YouTube? Oui, oui, on entend. Vous entendez sur YouTube? Nickel. Super. J'ai éteint les micros pour économiser leur batterie. Ouais. Et en soi, là, on a fait tout. On est bien sur YouTube. Ok. Là, vous m'entendez? J'ai allumé le micro. Donc, normalement, on est censé m'entendre à un moment. Et ce moment est maintenant. Ce moment n'est toujours pas maintenant. Niveau cadrage, c'est bon, il faut décaler un peu. Parce que je vais peut-être genre basculer un peu en arrière et tout. C'est bon quand même. Oui. On entend bien? Nickel. Ouais.
Le petit nœud vert est incroyable. Ah oui, ça va. On prend une place. Le problème, c'est les gens que en premier, je réponds non.
Naturel.
Pardon? Ah, pardon.
Pardon? Très bien, parfait. Ça va? Oui? Non, après, c'est peut-être bien si on fait un check pour être sûr qu'ils nous entendent. Genre, si tu les vois, qu'ils te font tous en l'air pour dire qu'ils nous entendent, c'est bien. Parce que... Ouais. Hi, Christina. Hi, Will. Can you hear me?
Yes.
Loud and clear.
Nice to meet you. Could you hear us?
Oui, eux, c'est normal, ils ne parlent pas pour l'instant.
Et le milieu, c'est l'au-delà.
C'est pas grave, c'est parfait. Eh bien,
C'est Rosa.
alors, il faut demander, alors pour le coup, il faut demander qui sont.
Oui, les Christina sont en ligne, ils nous entendent bien.
Très bien. Alors, on y va. Alors, bonjour à tous. Nous sommes ici réunis pour écouter Elsa Hénault pour sa défense de thèse. Et donc, je vais commencer par présenter le jury. Puis ensuite, vous allez nous présenter vos travaux pendant à peu près 3/4 d'heure. Et enfin, il y aura une séance de questions et de réponses qui seront discutées ici, donc, comme d'habitude. Donc, le jury est composé donc en ligne de Maria Cristina de Santis, qui est du Space Astrophysics and Planetology Center à l'INAF, donc Italie, qui est rapporteuse du manuscrit. Il y a ici Sergio Iopolo, qui est du Center for Interstellar Catalysis in Aarhus, Danemark, et qui est également rapporteur. On a Sonia Fornacier, ici présente, qui est professeure au LIRA, l'Observatoire de Paris et à l'Université Paris-Cité, je crois. On a William Grundy, qui est en ligne, qui est du Lowell Observatory. Nous avons donc en invité au jury Noémie Frisia Alonso, qui vient de Oviedo en Espagne. Et la thèse a été encadrée par Rosario Brunetto, de ce laboratoire ici, de Zaya Joabi, également du laboratoire, et de Donia Bakouti, maître de conférence à Paris-Saclay, à l'IAS aussi. Voilà. Quant à moi, je suis François Dulieu, du LIRA et professeur à Civil Service Paris Université. Donc Elsa, avec toute cette introduction, on vous écoute pour environ 3 quarts d'heure.
Merci. Et on va passer en anglais pour cette présentation. So, hello everyone. Thank you all for being here, and especially many thanks to the members of the jury for agreeing to review my thesis. I'm very happy to be presenting today the work I did during my PhD here at Institut d'Astrophysique Spatiale, working with Rosario, Zaya, and Donia. And I worked on the spectroscopic and chemical study of trans-Neptunian surfaces. And I will just hide this very quickly. So I will begin this presentation with an introduction on the trans-Neptunian objects, why they are interesting, and what was known about them when I began my thesis. So in the faraway regions of our solar system exists a big population of objects, which was first discovered as such about 30 years ago. And this region was visited by the New Horizons mission, which explored the Pluto-Charon system. Pluto being one of the handful of big objects with diameters above 1,000 kilometers. New Horizons then ventured further out and flew by this small bilobal object called Arrokoth. And these objects are referred to as trans-Neptunian objects, TNOs, because they orbit mostly outside of Neptune. Here you have a representation of known TNOs with their distance to the Sun and their inclination with respect to the ecliptic plane. Objects are represented according to their size, and you can see that the majority of objects with well-known orbits are not big TNOs, but are medium-sized, so with diameters between 100 and 800 kilometers. The trans-Neptunian region has a very complex dynamical structure. Some TNOs are in mean motion resonances with Neptune. Others are detached from Neptune's influence, while others are currently scattered by Neptune. And this specifically can feed into a centaur population, which are objects which orbit within the giant planet region. And these ones are a source for the Jupiter family comets, so the low inclination short period comets. Going back to TNOs, many inhabit this region called the classical belt, which was where the TNOs were first hypothesized to exist. We can summarize all this with a hot population, which is dynamically excited, contains the dwarf planets, the big TNOs, and is the most populated and thus most massive. In contrast, there is a cold population, the cold classicals, which are dynamically cold, have a different size distribution, typically devoid of big objects, and being less populated, they are less massive. So how can we explain such variability in terms of sizes and orbits of TNOs? Well, to understand this, we have to go back to the formation of the solar system more than 4 billion years ago. And this all started in a dense molecular cloud where only 1% of matter is solid and in the form of dust grains that are coated by ices. Following gravitational collapse, a star is born, and in its wake, a protoplanetary disk where physicochemical processes are rich and complex. In the disk, temperature drops as the distance from the star increases, and this will induce chemical gradients. So outwards of a so-called ice line, volatiles can be present as ices and be incorporated during planetary formation. Planetary formation occurs in different steps. Dust grains form aggregates and pebbles by collisional growth. Then planetesimals are the result of gravitational collapse. And further accretional processes can form fully fleshed out planets, which undergo differentiation, triggered by heating from the decay of radioactive isotopes. And such evolutionary processes effectively conceal the information regarding their initial chemical composition. But the medium-sized TNOs, they're planetesimals, so left over from incomplete planetary formation. And specifically, they are likely small enough to avoid big evolutionary changes induced by radiogenic heating, but they are big enough so that they're not collisional fragments. Thus, medium-sized TNOs likely still hold very valuable information regarding the physicochemical conditions in the early solar system. And understanding these TNOs helps us understand our primordial solar system. So the planetesimals, they likely constituted a massive disk which interacted with the neighboring planets. And here you can see a top view snapshot of the solar system across time. This primordial disk is scattered by the outwards migration of Neptune, possibly alongside a giant planet instability in a NIST-like scenario. And the population of TNOs that is observed today, they are only the few and far between remnants of this primordial disk. This migration shaped the current dynamical classes of TNOs, with hot populations having formed inwards and then being scattered and implanted outwards. And this scattering effectively mixes objects that formed at different distances and thus likely had very different composition. But interestingly, the cold classicals are the only preserved population thought to have been formed and maintained in place relatively unaltered. And thus they serve as a crucial anchor point for physicochemical processes at the edge of the solar system. So considering this formation scenario, what can we expect about the composition of TNOs? Having formed in cold regions, they must have accreted many volatile phases, and typically the ices that are present in dense molecular clouds or in protoplanetary disk. And among these ices, water ice is always the dominating ice, and then follows carbon monoxide, CO, carbon dioxide, CO2, methanol, ammonia. And these volatiles are also abundant in the gas emission of comets, descendants of TNOs. TNOs are also expected to contain variable amounts of dust, similar to cometary dust, that has been shown to be made of roughly equal parts of mineral and organic phases. So how can we get information about the composition of TNOs and validate this hypothesis? Well, a prime tool to uncover composition is to study how the sunlight is reflected from their surface. Because indeed, how much a surface reflects or absorbs the light is indicative of the material that composes it. And TNOs are observed most easily in the visible, where you have here a schematic representation of typical spectra, which are featureless, and can be described by using simple parameters like a spectral slope, which would show how neutral or how red an object is. When we look at the distribution of spectral slope versus albedo, so how bright an object is, you really can clearly see the emergence of two distinct surface types, because indeed you have some objects that are dark and neutral, while others are bright and red. So we have color as a first characterization of TNO surface composition. And with this, it's possible to decompose this global bimodal distribution of colors into the different dynamical classes that constitute the TNOs. And this was done by various independent studies and surveys, all consistently finding that cold classicals are homogeneously red, while the hot populations show both neutral and red objects. So coupling this information with dynamical models supports the idea that a color and thus a compositional transition existed within the primordial disk that was scattered. But colors do not allow for the clear identification of any chemical species, so TNOs are also observed in the near-infrared range, where absorption bands can be clearly detected and attributed to certain compounds. So here are examples of the variety of spectra that can be obtained for TNOs, starting with Pluto, the biggest ones, with its clear features of methane ice. Going down in size, you have Quaoar here, which shows prominent features of water ice, specifically crystalline ice. Next, going down in size, objects are smaller, so these spectra are more noisy. And typically, the majority of them are featureless, like this one here, where no ice identification is possible. When features are observed, they are mostly attributed to water ice with the typical 1.5 and 2 micron band here seen on the center folus. And folus is interesting because it also has an absorption here attributed to methanol, as is the case for the cold classical Arrokoth. These variations in composition can be explained on first order by the retention of surface volatiles. And this retention will depend on the temperature of an object and thus its distance to the sun. It will then also depend on the mass of the object and on the mass of the molecule to retain. So objects that are big enough or cold enough can retain the most volatile ices, as is the case for Pluto, while our medium-sized TNOs could only retain the most refractory ices, being water ice and methanol. A final important factor to take into account when studying the surface composition of TNOs is that TNOs are atmosphereless, so their surfaces are continuously exposed to a flux of ion, which can be dominated by low-energy protons within the heliosphere or by higher-energy protons in the local interstellar medium. And these ions will penetrate to different depths, depending on their nature, their energy, and the nature of the surface. And ions will lose this energy by electronic and nuclear interactions with the surface material. And this will result in many things. First, sputtering, so the ejection of material which erodes the surface. And structural changes to the ice, which are typically amorphization and compaction, which are very well studied for water ice. And then finally, you have some chemical changes, so the destruction and the formation of certain species. But a long-standing question in the community was to understand to which extent does this energetic processing effectively modify the surfaces of TNOs, and specifically its spectral properties. Because if we understand these effects of irradiation, we can try to go back to the initial chemical composition of the surface. So to address this, laboratory experiments have to be run and compared with observations, however limited these observations may have been. And so far, major results concerned color changes and typically the reddening of irradiated methanol ices, but also structural changes of water ice probed through a crystalline to amorphous fraction. Okay, so now let us recapitulate what we know so far about the trans-Neptunian region. New Horizons has shown that big objects like Pluto are rich in volatile and are very geologically active with surfaces that are refreshed by various processes, while the small objects like Arrokoth have more refractory surfaces, more primitive, more older, and they likely still hold physicochemical information regarding their formation process. Majority of known TNOs, which are the medium-sized TNOs, so with diameters between 100 and 800 kilometers, and they really are the prime subjects to understand the physicochemical conditions in the outer part of the young solar system. And their surface characteristics can be summarized as such, with neutral versus red surface types, which are thought to be primordial. Water ice features being the most widespread, but then limited parameters to really assess and understand the irradiation effects. So the broad questions that have guided my thesis were simply to address what is the actual surface composition of TNOs, and what story will this composition tell? Will it be testament to primordial characteristics, or rather to evolutionary processes? And to address these questions, it is a necessity to work with new infrared spectroscopic observations that would be better in terms of signal-to-noise ratio, but also that would allow for an extension of the wavelength range. And this is only possible with infrared space telescopes. Additional laboratory work are also required, specifically with temperatures, irradiation doses, and spectroscopic configurations that are most relevant for TNOs. And I have worked on both these aspects during my thesis, and particularly on how they can complement each other to really enhance our understanding of TNO chemical composition. So my introduction is now over, and we will start to look at the results, starting with the observational side. Okay, so the observations. The James Webb Space Telescope, whom you might have heard of, is very famous for its 6.5 meter wide primary mirror. It was launched in late 2021 and reached its working position in the second Lagrangian point. And among the 4 science instruments on board James Webb, the NIRSPEC instrument is of the highest relevance for the spectroscopy of TNOs. It allows access to the full range from 0.6 to 5.3 microns, and specifically the first-time access to wavelengths above 2.5 microns. And this makes, for the first time, the detection of fundamental vibrational bands possible. And different configurations are possible depending on the targets and the aims of these observations, and where increasing the spectral resolution will decrease the sensitivity. And while James Webb is more famously known for looking at distant galaxies or exoplanets, it does spend about 5% of its time looking at solar system objects. So during the first cycle of JWST observations, the DiSCo-TNO large program, led by Noemi Pilena Alonso, who's here with us now, proposed to sample the diversity of medium-sized TNOs with NIRSPEC prism in the integral field unit mode. And this program remains to this day the only large JWST program for solar system science. Targets were chosen to maximize overlap with the TNOs are cool survey, which provided diameter and albedo measurements for many objects. The 54 TNOs that were observed in this program were chosen to sample from all albedo, all diameter, and all spectral slope in the visible, but also all dynamical classes. I joined this collaboration in summer 2022 when we were preparing for the first observations to occur, and observations ran for close to a year. Targets are point sources within the field of view. So the spectra are extracted with a template point spread function, routine over background subtracted slices. And in this field of view here, you can see 2 sources, which are the resolved components of the Morse and Somnus binary, which is widely separated. So now on to the results of this program. A major result from the DiSCo-TNO program is that we found TNO surfaces to define 3 main spectral and compositional groups. So this means that of the more than 50 TNOs observed, they all fit into one of these 3 big categories. And these were found using independent clustering techniques, which grouped the spectra according to their similarities. Ultimately, these groups were nicknamed based on the shape of the prominent 3-micron band, with the bold type, the double dip type, and the cliff type. Other than the 3-micron feature, we can see other distances, for example, changes in the slope in the visible to near infrared range. So now let us dig deeper and see what each group is made of. And this band attribution work was a major aspect of my contribution to this paper. So starting with the bold spectra, they are dominated by features of water ice, with indication of crystalline water ice in the shape of the 1.5 micron band, and also with the intensity of the Fresnel peak here, which is within the OH stretching band at 3 micron. Then we also detected the asymmetric fundamental stretching mode of CO2 here within this broad water ice feature. Now on to the double dips, on which the strongest features of CO2 are observed, with here the fundamental band having a quite peculiar shape. The high abundance of CO2 is also evidenced by the intensity of the combination band here at 2.7 micron, but also by the strong detection of the isotopologue 13 CO2. Next, we can see here quite a growing contribution of CH stretching modes in aliphatic organics. And finally, the last interesting aspect of double dips is this strong sharp feature here, which is attributed to CO ice. Now on to the last group, the cliff-type TNOs. You can see here a much stronger contribution of the organics, with the CH band being really deep. You can notice big differences with the double dip groups, specifically in the amount of CO2 ice, with the fundamental band showing a more classical profile. We also detected CO ice in the cliffs, but this feature is overlapped with nitrogen-bearing species, which we attributed potentially to the cyanide ion or nitrile function. Okay, so we now have a complete picture of the new chemical composition for TNOs, and within this picture, we can see that no group seem to be representative of interstellar or cometary ices. But CO2 ice being detected on every TNO becomes the most widespread ice. So we can take a closer look at the absorption bands of CO2. So in ball-type spectra, the shape of the fundamental band of CO2 can be modeled by small CO2 grains intimately mixed within dusty water ice, so water and silicates. And the peak position of this band also agrees with CO2 being mixed with water ice. In double dip spectra, the shape of the fundamental band came as quite a surprise, and is to this day impossible to fully reproduce with current light scattering models. But we do know that a combination of factors likely contributes to this double-peaked feature. We need a high abundance of CO2 so that fine optical properties come into play. Very fine grains of CO2, so with grains smaller than the wavelength, and a certain assembly within the medium to favor drops or rises in reflectance. But there is a need for refined light scattering models to fully explain the physical structure of CO2 grains. And in this study of CO2 absorption features, I was particularly interested in the 2.7 combination band. This feature is absent on typical ball-type spectra, but can be studied on cliffs and double dips. And variations within this combination band can be more easily interpreted than those of the fundamental band. So I extracted the band depth, representative of the intensity of the feature, and the peak position. And both these parameters are represented here. Please ignore the symbols and just focus on what is circled here. And you can start to see very different behaviors with our double dips all being clustered here with high band depth, so intense features, and with peak positions that are shifted to low wave numbers. And when you compare this with laboratory spectra, which are the values reported here as the vertical lines, you can see that the CO2 on double dips matches nicely with pure CO2 or CO2 with a bit of CO. On cliffs, it's completely different. The band depth is much weaker, and the positions are shifted to higher wave number. And when you compare this with laboratory spectra, you see that it matches CO2 being mixed in a polar compound, either water ice or methanol ice. So really from this graph, we can summarize a high variability in CO2 abundance, but also a variability in chemical environment, with CO2 being mostly pure on double dips, but mixed in polar compounds for the cliffs. Okay, so going back to the spectral types, we can try to investigate the origin of the three groups. And we looked at the groups in relation with different physical parameters. Here you have each object dispersed against albedo and diameter, and they are colored according to their spectral type. And we can see that some link between albedo and spectral types are emerging, because indeed the ball types are found predominantly for the low albedo objects, whereas the brightest objects are all cliff and double dips. But the most striking result from this graph is that there is no correlation between diameter and compositional group, because indeed you can take an object of any size, let's say 400 kilometers, and it can be either a ball, a cliff, or a double dip. So this indicates that in this size range, surface composition is not related to size-dependent internal processes, contrary to what is seen on dwarf planets. So we have to look at other parameters to explain the existence of these three different compositional groups. So we looked at composition in relation to dynamical parameters. And in this graph of inclination versus semi-major axis, you can start to see that the most dynamically excited objects here are predominantly from the ball and double dip compositional group. It's easier to link for links by looking at the distribution of compositional types within each dynamical class. And the most striking thing to notice is that all the cold classicals are cliff type, whereas the other dynamical classes do not have the same distribution and have really a mixed composition with a predominance of ball type and double dip type. And so this really is a direct result from mixing during planetary migration. So we now have a strong indication of a primordial origin for the compositional types. And this can be represented like this, where objects are represented according to their spectral distance to the average cold classicals, because remember, the cold classicals are our anchor points for having formed the furthest out. And then on the y-axis, you have an indication of the free molecules that really define these groups, with water ice being dominant in the ball, CO2 ice dominant in the double dips, and methanol ice being dominant for the cliffs. And these spectral distances are likely related with the heliocentric distance before planetary migration, indicating sharp compositional variations within the primordial disk. And such clear differences would need a sharp process to create them. And this process could be retention lines at the surface of planetesimals, with objects being formed inwards only being able to retain water ice, the most refractory, while objects having formed furthest out could efficiently retain methanol, consistent with the cliff, with the cold classicals being cliffs. Okay, so far we have shown that TNO surfaces fall into three main compositional groups. And I have shown that these are closely related to variations in abundance and chemical environment of CO2. And these compositional groups likely represent how close the TNOs were to the sun before planetary migration scattered them. So we now have a new paradigm in how we think about TNO surfaces, and investigations into surface aging processes become specific to each group. And so in this new framework, there were particular points that I wanted to address. The first being the study of CO ice, and specifically putting some constraints on the origin of this CO ice. And the second point I wanted to address was about the link between a methanol detection and the very red color of those TNOs. So I will now switch to other results that emerge from these two questions. Okay, so starting with the case of CO, which we detected on the double dips and the cliff objects. CO does not really fit into a retention line scenario because it's too volatile to be retained by our medium-sized TNOs here between 100 and 800 kilometers in diameter. Moreover, more sophisticated thermal evolution models also conclude to a depletion of CO at the surface or even within the bulk on short timescales, so 200 million years, compared to an object's lifetime of 4 billion years. So we need to invoke sources of CO that are not a primordial heritage. And specifically, I investigated a radiolytic origin of these CO ices, so the production of CO ice from the irradiation of TNO surfaces. So I began by studying the distribution of CO ice on TNOs, typically using the band area extracted here. And I looked at CO in relation with CO2, and CO2 being studied by its 2.7 micron band, from which I extracted also the area and the peak position. I used the ratio between the two band areas, and which, when you balance them with the band strength, you can get close to an estimate of the relative abundance between CO and CO2. So this was for the observational side, and now we can have a look at the experimental side. So to simulate the energetic processing of TNO surfaces, I used the Ingmar chamber, which is here, coupled to the Sidonie ion separator, which is in a building just next door. Ingmar is a high vacuum chamber interfaced with a cryocooler, and this allows to cool a substrate down to temperatures that are relevant for TNOs. So a typical experiment would begin with ice deposition. So the ice is formed by the condensation of a gas that is prepared in a mixing chamber, and it will condense on the substrate, here cooled at 45 to 60 Kelvin, that I've chosen to represent the TNOs, which is much higher than the temperature that is used for the interstellar medium ices, which are the most widespread type of experiments. Once your ice is formed, you can irradiate it. And here I have chosen to work with protons at 30 kiloelectron volts. And this allows me to probe the electronic stopping power, which is thought to dominate the dose deposition on TNO surfaces. Oops. And then we can probe the physicochemical processes that are triggered by irradiation by using infrared spectroscopy, most typically done in transmission mode. Okay, so looking at some spectra from these experiments, I ran two template experiments, one with ices dominated by CO2 to reproduce template double dip chemistry, and one dominated by methanol to reproduce a typical cliff chemistry. And so in black, you have the initial ice, and then in color, different irradiation steps, where you can see here for the methanol case that you destroy the methanol, form water ice, and form other species, typically CO2 and CO. CO is also formed here. So in both cases, we form CO, and CO remains trapped in the parent ice, even above its sublimation temperature. From these spectra, I extracted the relative abundance between CO and CO2, which is this parameter here, and I've studied how it evolves with increasing irradiation dose. And you can see here that the ratio increases until reaching a stabilized value. But interestingly, this value depends on the temperature of our experiments, because indeed, if we summarize this, you have the low temperature experiments, which have high CO2, CO2, and the higher temperature experiments, which are lower here. Looking at the same thing for the methanol experiments, so you have again the relative abundance of CO and CO2 versus dose, and this time the ratio decreases until reaching a stabilized value, which this time is not really dependent on the temperature of the ice. So now that we know the behavior of these ices and their irradiation, we can compare them with what we observe on TNOs. So starting with the double dips, this is the mean value of the CO-CO2 ratio for the double dip objects, and you can see that it matches very well with my irradiation experiments at 45 Kelvin, once you reach a certain dose to have this steady state. For the cliffs, you have here the mean value of the cliffs, with the dispersion being a bit higher, cliff surfaces being less homogeneous than the double dips. But we can see again that the cliff value matches very nicely our experiments of irradiation of methanol, once again, once you reach a certain dose so that you get this steady state. So this was the mean value. We can have a look at what happens with individual objects, where you have again the CO2-CO2 ratio for all the individual objects, and that are spread using this the position of the CO2 combination band, which, as I have shown you before, is a very nice indicator of the chemical environment of CO2, with the double dips being consistent with being pure or mixed with a bit of CO, whereas the cliffs are more consistent with being mixed in a polar component. So this really separates the two groups very well. And when you overlap the results of my experiments on this, you can see that we reproduce the different two types of chemistries very well. So my main result is that TNO surfaces are compatible both in terms of relative abundances and chemical environment, with CO being entirely secondary, so being formed by CO2 irradiation on the double dips and methanol irradiation on the cliffs. So now that we have some indication of irradiation, we can try to look for variations within this irradiation. So for this, using again the CO-CO2 ratio, but this time spreading objects according to their aphelion, so an indication of how far these objects venture outwards, and possibly crossing into the local interstellar medium, where they can experience an increase in galactic flux, which will deposit energy much faster than, let's say, at 40 astronomical units. So looking specifically at the double dips here, which probe nicely these different regions, we see no variation of the CO-CO2 ratio with aphelion. And this is a good indication that a steady state is likely reached on all our double dip TNOs. But these broad variations for the cliffs might be more related to different initial compositions than variations in irradiation. Moreover, for the double dips here, when you consider the depth that is probed by the infrared photons that give us this CO-CO2 estimate parameter, they only really probed the first few microns of the surface, whereas the cosmic rays will penetrate much deeper and deposit a lot of their energy to layers that are not probed by the spectroscopic observations. Okay, so my main result from this is that the TNO surfaces are consistent with an irradiation origin of the CO ice that we detected. So now we can have a look at the final point I was interested in, and it's the link between methanol detection and red color. This link was observed, has been observed for a while. With here, you have the spectra of Arrokoff in black, which is overlapped with the modeled spectra of Pholus and another object, which show this strong 2.27 micron feature associated with methanol. And all of these have very steep red spectral slope in the visible to near infrared range, which in the models can be explained by the incorporation of organic compounds. And this was also consistent with the fact that the reddest taxonomic group shows absorption at 2.3 micron, consistent with either methanol or organics, when the quality of the spectra could not allow to disentangle between the two. And these links are now confirmed with the GWST observations, where you have here a representation of the spectral slope with the objects colored according to their spectral types. And you can clearly see that all the reddest objects are cliff objects. So within this, I was specifically interested in investigating methanol as the precursor of the reddening agents, which could be organics formed by the irradiation of methanol. So in my experiments, I studied within the methanol reach experiments, I studied the relative abundance between methanol and water, which is seen here to decrease with increasing irradiation dose, which is a testament to the efficient destruction of methanol while water ice is produced. And when you compare the evolution of this methanol content with the relative abundances that were found from Hapke modeling of these three objects here, you can see that their high methanol content can only be sustained for surfaces that have seen less than around 40 electron volts per molecule, so quite low irradiation doses. So this was for the molecular aspect, and then I wanted to probe color in the laboratory. And this is a bit more tricky because you need to have ICs that are thick enough so that you can probe them ideally in the reflectance mode, to get as close as possible to what is the observing configuration for the TNOs. And so to have thick ices that are homogeneously irradiated, we do this trick where we deposit the ice and irradiate simultaneously. And then the result can be probed by reflectance spectroscopy. And this was previously shown to starting with methanol ices that are transparent in the visible to near infrared range to show this really reddening slope with increasing irradiation dose. And so I've studied the same thing for my experiments by using the JR slope, which is the normalized reflectivity gradient between the 0.68 and the 1.5 micron photometric bands. Parameter is represented here versus the increasing irradiation dose. And you can see that the slope increases with increasing irradiation dose, but this efficiency will depend. This efficiency of the reddening will depend on the initial ice composition, because indeed this trend here was obtained for pure methanol, whereas when you study methanol mixed with water ice, you form much less red ices. So now we can compare these slopes with the ones that are observed on the free objects, here with quantified methanol content, and here the objects from the DiSCo program, which show the deepest absorptions of methanol. And we see that roughly these colors can only be produced at high irradiation doses, so at least 150 electron volts per molecule. But if you remember what I just said 2 slides earlier, it's that the methanol content can only be sustained for low irradiation doses. So how can we reconcile these 2 parameters? Well, we have to think about the penetration depths of the photons within the surface. So this JR slope parameter comes from photons that only penetrate to at most tens of microns within the surface. And they give indication of high irradiation doses. Whereas the methanol content comes from photons that penetrate much deeper, hundreds of microns within the surface, and they give an indication of low irradiation doses. So I found that photons probe depths that are affected differently by irradiation. And this is completely consistent with what is found from numerical simulations that integrate all the ion flux that is received by a TNO surface during its lifetime. And while the models vary a bit, they all consistently find an irradiation gradient within the first meter of the surface. And specifically, this estimation that was done for Arrokoff here gives those estimates that are in very good agreement with mine. So here I can conclude by saying that the red surfaces of TNOs can be fully explained by irradiation processes on initially methanol-rich ices. And so this suggests that there was an early enrichment in methanol compared to interstellar and cometary abundances. And this could probably occur in the same process that shaped the free spectral groups. Okay, so now on to my conclusions of this presentation. I have started by explaining how we discovered the existence of 3 main spectral and compositional groups, which are likely related to their heliocentric distance before planetary migration. And specifically on these objects, I have studied their CO2 abundance, which is lowest on the balls, highest in the double deeps, and medium on the cliff. And these variations in abundance are correlated with variations in the chemical state, where here CO2 is mixed in water ice. When it's most abundant, CO2 is pure. And then finally, CO2 is mixed in polar compounds on cliff-type surfaces. Now, focusing on just the objects that had a CO detection, I found that ball and cliff surfaces are consistent with CO being secondary and formed by the dominant ice on each surface type. Now, again, focusing on just the cliffs, I have investigated the reddening of irradiated methanol ices, and specifically I found that the JR slope and the methanol content of TNOs match an irradiation gradient. And so with these two works, I have found a consistent set of parameters that testify to the extent of energetic processing on TNO surfaces. And this will allow to eventually retrieve an initial ice composition of TNO surfaces. Now, perspectives with the current DiSCo-TNO dataset. We could look for complementary evidence of irradiation. We could also look for hints of other primordial differences. Specifically, we investigated subgroups within the cliffs that are defined by variations in methanol content. And I was also very interested to look at the nitrogen-bearing compounds. And this is why I co-supervised the internship of Sasha, who now started her PhD with us. And then the ultimate goal is also to really make some links with the TNOs and other small body populations, the easiest ones being the centaurs, where we found bull centaurs and cliff centaurs, but maybe an underrepresentation of double dips, which begs the question of the survival of a CO2-rich surface. Now I will just leave you with this kind of DiSCo-TNO picture of the outer solar system, which will be filled with a lot more objects coming from all the different observations that James Webb is currently doing. And with this increasing number of observations and coupling this with dynamical simulations, ultimately the goal is to uncover the primordial distribution of these molecules within the early solar system. And so my presentation is now done. I want to thank my many collaborators here at IIS, with also, of course, the Sidonie team, and of course, the DiSCo-TNO program, and especially Noémie for welcoming me into the team, and also the group on the methanol color. And I will just leave you with this slide of the other activities I led during my thesis. Thank you.
Thank you, Elsa.
Okay, I switch off my mic and you switch.
Okay, okay. Can you hear us now?
Yes, could you hear me?
Okay.
Okay, thank you very much. Because I think that both the microphone was on, but I cannot hear you, Rosario.
Okay, can you hear us now?
Yeah.
Okay, great. So we're gonna move this around so that it gets closer.
So please, Christina, you have the floor. You can ask your question to Elsa.
First of all, I want to congratulate with Elsa with this magnificent work for this PhD thesis. Very, very, very interesting, and I would love to speak with you for the rest of the afternoon, but I can't. So I will ask you a few questions that I hope could be answered quite easily but more or less our curiosity. As you may know, I'm always very interested in the ammoniated ices, in the ammonia stuff. So I would like to understand the reason why, even if the NH3 ice are foreseen from the modeling of the condensation retention line, we see really a little bit of this kind of ice on the spectrum. At least all the ammonia ice is embedded in the larger water bands, but I really do not see too much ammonia in the spectra that you have shown before. This is one of the questions that I have. If you have any idea about the reason why we do not see huge amounts of this kind of ice.
Yeah, this is a very nice point. We were also kind of not surprised, but yeah, we noticed, oh, there's no clear sign of ammonia. There could be within the cliff group with this shape
Elsa,
of the free micron band.
Ce serait bien. Here.
With the shape of the free micron band that is really different from the double dip and the cliff. So that could hide some NH stretching features within it. We could also start to look for some evidence of NH features at 2.2 micron, but this is a kind of a low resolution region where it might be hard for now to really disentangle the contribution between the CH and the NH. But we do have maybe a hypothesis for why we don't see a strong ammoniated signatures. And this is because ammonia can be really easily destroyed by irradiation, kind of like methanol, where we could see its irradiation products. So maybe NH3 was the source for the OCN and the CN that we're seeing on the cliffs. So this could be a reason, but also maybe just a low abundance in ammonia in the first place. But yeah, this is definitely an interesting thing.
Okay, thanks. May I ask you something else?
Yes, sure.
Okay, so I have another question because I can understand the fact that the CO2 is destroyed. Let's put it this way: the CO2 can be sublimated away, and you need a replenishment of this kind of ice, and the radiation processes are good processes in order to get this ice on the surface of this irradiated object, and you can trap the CO2 in the ice. This is what, if I well understood the process that you have tried to simulate with the radiation of this kind of ices. At the same time, I was wondering the reason why we could not expect this kind of process. So trapped CO2 in the primordial combination of the ice. I don't know if I explain myself. It's a little bit. I don't know if you understand.
CO ices.
Sorry?
Are you talking about CO2 ices or CO ices?
I'm talking about the irradiation that you performed in order to explain the kind of different ice that in principle should not be there due to sublimation rate.
Mostly the CO ice, yeah.
Yeah.
Well, this is really concerning the outermost surface that we expect to be the most heavily impacted by insolation and to have undergone quite a strong heating that would really effectively quickly deplete a primordial CO inventory. But we don't discard any persistence of CO ice within the bulk. that could remain trapped within water ice, CO2 ice, or any kind of refractory material. So my work was to mostly explore one scenario and see if it matches the observations. And so it's the case. So a full irradiation origin for CO is possible.
Okay, so but in this case, in any case, you cannot exclude the fact that this kind of CO trapped, because in any case, you need to trap the CO.
Yes.
Also for the radiation, with the radiation mechanism, you
Yeah.
need to trap, otherwise you lose the CO very, very quickly. So so you cannot exclude that part of the CO that we actually see is trapped since the beginning.
We don't exclude it, but if it's there, it must be very minor, because the irradiation formation path is so efficient. But then there are some thermal models that do not only model pure CO ice, but CO ice mixed within water ice, or even CO2 ice. And in some cases, the CO can be depleted even when it's mixed.
Okay. Okay, thank you very much.
You can ask another question if you wish so.
Oh, well, I have to say that I have some other few questions, but more related not with the presentation that Elsa have done right now, but with some figures on the thesis. So I don't know if it's the case to ask. Maybe I can ask also after.
Do you have your PDF manuscript or the
PDF or the
so
we can talk about the thesis now.
Yes.
Really? Okay.
Yeah,
So because okay, thank you. Because I have a couple of questions only to understand. For instance, if you go to figure 4.3, and it seems to me that in the thesis you write that you do not see any dependence with the diameter and the CO2 band depth, yes, and with the slope also. So I see a strong correlation between slope and the CO2 band depth, but I do not fully agree on the fact that there is a sort of independence of the CO2 band depth with the diameter. I see a sort of increase till 400, more or less, and then a sort of steady state. I'm not sure about, of course, but I don't know if you can elaborate a little bit more about that.
Yes, so the relationship that was tested between the CO2 band depth and the diameter was mostly for a linear relationship.
Okay.
This is a linear relationship was not statistically significant. But
yes, sure.
Maybe we could try to investigate if there is, as you say, towards the low diameters, maybe an increase and then a steady state once you go over the 400 kilometer range.
More or less.
But maybe this would need more objects to.
Yes, sure. I think that the statistics is still not sufficient to discriminate between these trends, but I don't know. It seems to me simply looking the data is simply looking the figure that there is something, a sort of increase, and then again a sort of steady state that could be possible.
It also evokes the question of the existence of these free spectral groups to smaller sizes. With objects like Arrokoth, would these groups still be valid? So this is something to explore.
Okay. So thank you very much. I think that for me is sufficient.
Thank you very much again. And now we will ask Sergio to ask his questions, please.
Yes. Elsa, what a wonderful thesis that I have read. I really want to congratulate with you because And I read few of those theses, but yours really outstands for clarity, for quality of the content, and the quality of the figures and the science that you carried out in just a little bit more than 3 years. This is really amazing. So congratulations. So now then the challenge was on me to find questions for you, because every time I thought, oh, I don't understand this, why is that? Then the next sentence was the answer. So it was really difficult to come up with good questions. Nevertheless, I tried to find a few just because I really had to. So I was really intrigued by this hypothesis of the retention lines versus the snow lines. Initially, I looked at the figure and I thought, look, well, those are snow lines, but they are completely scrambled. What's going on here? So, and then you write about this, I guess it's inspired by the Mike Brown paper from 2011. Yeah, this one right there. But still, there is something that is not fully clear to me. So maybe I would like you to talk a little bit more, and to go a little bit deeper into this theory, because you say that CO2 is heavier, it's a higher mass than methanol, and it should be retained at the inner part compared to methanol. However, how about water? Water is lighter. The water in this scheme, in this model, and in your theory here, your hypothesis is actually even closer to the sun. So is there something special about the water ice, or is it something missing? Another point that I was also struggling to understand is that based on your results, there is no mass dependence. So you say that the is a gravitational effect, but that it links to the mass of the object, but there is absolutely no mass dependence there. So can you please make me understand a little bit more?
Yeah, it's, I guess it's not clear for us either, for different factors. So initially, we could imagine that, for example, all the ices could condense. You're between most, you're below, beyond most ice lines, and so you have an initial composition that is interstellar-like. But then this is only within the disk, so you still have a lot of gas. And then once the disk cleared, you have all these surfaces of planetesimals that are exposed for the first time to strong insolation because they're quite close to the sun before they're scattering. And so this is when the retention lines would be set, so after an ice line. And so, as you said, the objects formed that are furthest in, once they are exposed to the sun, could only retain water ice within this retention scenario. And this retention scenario is not only based on the mass of the molecule, but also on its volatility. And so even though water ice is not as heavy as CO2, it is still the most refractory ices due to its network of hydrogen bonds.
But methanol, if I can interrupt, is heavier. And so why is that? And also the desorption temperature of methanol is not that far from water. So is it, that's what I'm just thinking. Is it because the wedge bonding network the water can create is a stronger network than what you can get from methanol?
Probably.
Which is also a polar molecule, but in a sense, but is there something to do with the chemistry, with the physics of these ices, versus like an apolar molecule like CO2?
Yeah.
Or?
The problem is that all of these are kind of big questions that were not really addressed in any models or in any theory before. So this will have to be addressed now that we have these three types and that we're looking to explain them. So we need more models that are more sophisticated than this retention one, which is just atmospheric escape with the pure ice in equilibrium with gas. And so there are, two things. The first being with the question of the diameter. As you see here, something should happen when you reach zero diameter. Like you have to have a limit, and this is really not taken into account within this model. So there should be a study as to when this gravitational pull dominates over the volatility of the molecule, because we could expect these two to switch once you go to very small diameters. And then the next elephant in the room is that why the cliffs that are here, so beyond this methanol line, would have a surface enriched in methanol, but would not keep water ice and CO2. So this is the big thing where we suppose it has to be with something of a segregation where you create some layers where there's different stages of sublimation and recondensation that would virtually enrich the surface into CO2 and methanol. And this was seen in older thermal evolution models, but it was mostly studied within the bulk, and it did not resolve the extreme surface that is probed by our infrared spectra. So kind of an incentive for further modeling and really thermal studies on this thin surface layer.
Excellent, thank you. That explains a little bit better. Okay, so then one of the main point of your thesis was to understand the origin of CO, and especially in your experiments and in the observations. And I was thinking, like, you do like a careful study of the position and maybe profile of CO2, but I was also looking at the literature a little bit, and there is some work from Penteado 2011, Kappen or 2011, something like that, that looks at the CO peak position as a function of the environment. You say that the CO formed further out is formed from the irradiation of methanol, and that's a clear sign of irradiation processing. And then there is the other group, the double dip, that is CO formed from CO2. And if you look at the laboratory data, then you see that actually the peak position of CO changes a bit depending on the environment. And there is, I think, even a paper from Gianni Stazzulla that looked at the position of maybe it was CO2. But in any case, for CO, the peak position would change whether it's in water or in methanol or in the CO2. And there is some data also in the LIDA database that you can use if you don't have it at end. Did you look into that or?
So the problem is not a lack of laboratory data. The problem is from the observational side, because this plot here ideally would have the CO benzene that, as we say, in different environments shifts, whether it is mixed in a apolar or polar mixture. And I also see this with my experiments where I have these values as well. So I did the same version of this plot, but with the CO position here. And so we do see that in the double dips and in the cliff, the CO position is different, with the CO bands being on the shorter wavelength range and on the longer wavelength range for the cliffs. So we really do see that the CO is indeed in two different chemical environments. But the problem is that it does not match with laboratory data. But we think that it's actually uncertainties in the wavelength solution of near spec beyond 2 micron, 4 micron, sorry. And this was seen in another study where they tried to rescale the wavelength range using an assumption that CO2 was pure and fixing this with the 13 CO2 band position. But just to be more conservative, we use this parameter, which we are sure matches the observations. But the CO band position from the observations right now, we consider to be a bit more uncertain. But we do see that they're distinct. So they have different chemical environments for sure, but it's not as direct to match it with laboratory data.
But in principle, if that will be fixed somehow, then you could actually cross-check and yeah. So then you show in I think slide 26 is the temperature dependence. This one. In one case, when you have this CO2 dominated ice versus temperature non-dependence for the methanol, do you know why in one case you have a temperature dependence? Why is it so sensitive to the temperature in one case and not in the other?
Yes. So we have some there were some studies that studied how efficiently CO2 ice can trap CO versus the trapping of CO in water ice. And they found that the CO2 ice was actually more efficient than water ice to trap CO, but only at very low temperatures. And once you are at temperatures that is above the sublimation temperature of CO, the restructuring dynamics must be different. And so it's much more stable in methanol ice, which is much more refractory than CO2. And that can trap better, maybe also due to its polarity, how it forms stronger bonds, which can trap CO, but it's not the case with the CO2 ice.
I see. Okay. If I can ask
One more.
one more? Yeah. So just figure 5.8, I think maybe slide 31. When you see the destruction of methanol. Yeah. Yes, this one. So here, then you extrapolate the dose for TNOs. And then I was thinking, you decided explicitly to restrict yourself to a certain range of temperatures based on the object that you observed, although you actually selected 60 Kelvin, and I think you only have one object out there. So that is a little bit strange. Why not 30 or 25? But that's one question. But then I also thought, okay, but then you also selected protons at one energy, and then you compare with protons or with other energies, and you didn't see any dependence there. But if you look a little bit deeper in the literature, when different ions, maybe heavier ions, especially sulfur ions, are used, then actually this slope changes quite a bit. So you selected, probably because of time or specific reasons, a small set of parameters. But if you would have explored a little bit more the parameter space, maybe you would have found other results. For instance, if you use the sulfur ions, you might have found another dose that would fit this the observations better or worse. I don't know. So the question is, why did you select only these? And are you planning, or is the lab going to do more systematic study of different ions or energies or temperatures? Also, the fact that whether the ice is amorphous or crystalline might change these results as well. So how strong and confident can you be on what you are actually saying here, laboratory versus observation, that this is the dose or not? Because I'm not sure that there is one answer. I think it's too strong of a statement. What do you think?
So maybe starting with the temperature aspect. So indeed, for the methanol experiments, most of them were carried out at 60 Kelvin, one at 35. And this is because when we started these experiments, we had kind of a different framework. I did these before we had the GWC data, and we're really more trying to work on the spectral flawless, which is a centaur and is a bit at higher temperatures than the TNOs. So this was to get closer to the centaur region. But we don't find a strong dependency with temperature anyway, so it can be also very nicely representative of the TNOs. And then for the choice of the ion, so of course there's a practical aspect in the choice of the ion. It's the bottle of gas that you have, and it's the energy range that is available here on the setup. But it's also the fact that with this ion, so with protons at 30 electron volts, it's really the electronic stopping power that dominates, and it's really what is thought to be the main, the dominant source of energy deposition on TNOs. So using this, we're not specifically trying to reproduce explicitly this ion at this energy, but just this dose deposition. So if we were to choose different ions, which also have this electronic energy deposition as the dominant regime, you would expect roughly at first order similar results. It might change a bit if you have the implantation of the ion here, when I've worked with the thick ices that are deposited and irradiated at the same time, we do implant dehydrogen. So this might compensate a bit of the dehydrogenation that occurs with irradiation, but it's also representative of what happens on CNO surfaces because the ions are indeed implanted within the surface. And hydrogen being the dominant ion for the solar wind, for solar energetic particles, and for galactic cosmic rays, we do believe that we are representing the major effect. But it would be interesting to study others for completeness and for potential models like numerical models, which which use the cross sections derived from different ions to paint the full picture and to see how much are these heavy ions really changing the surface. Yes, it would be nice to complete this picture, but I do think that we have a good first order idea of what's going on, at least on methanol-rich TNOs for this.
Thank you so much.
Now, Sonia, you ask questions.
Well, I have to repeat what Sergio says. I think the manuscript is simply excellent. It's well written, well structured, with high quality pictures, and with a number of bibliographic references that is very, very important. And the quality of the work is simply very, very good. I think it will serve as reference for me, colleagues, and students to study solar system body. The presentation was also extremely clear, so I have to find questions, and it's hard work. And I want really to congratulate with you and your supervisors for the job you did in these 3 years. You did experiments on irradiation of several ices, and you compare the band depth, for instance, of CO2 over CO. I wonder, did you look also at what are these effects on the spectral slopes and albedo of these bodies? Did you try to set up bigger pictures to see if irradiation match also what we see in the visible range and in the albedo of this body? Can you elaborate a little bit?
So in terms of albedo, it's hard for us to, from the setup we have, to really get an idea of the absolute reflectance. So because, for example, we use the substrate on which we deposit the ice as the reference, the background for the spectrum in reflectance. But then the ice can be more diffusive than this reference. So we don't really have an idea of the absolute level of reflectance
of experiments.
Yes, within the experiment that we have here. But we worked towards improving this, but I could not use it for this thesis. So in terms of albedo, it's hard to say if we brighten or darken the ice. But in terms of spectral slope, so I did this study for methanol ices. So with pure methanol and with methanol mixed with water ice. And I actually have more experiments where you have water ice as a dominant. You don't create any kind of slope, any kind of reddening. And then I also looked at pure CO2 ices, which do show some reddening, but not as much as the methanol. So we started to look at this, but we don't have a complete picture with all different kinds of ices, just for the methanol-rich ices. But this would be interesting to continue this work now that we have these three spectral types, being able to match the slope of each spectral type.
Okay, and as we are in this slide, the J minus R slope are J minus R filter, because I'm a little bit astonished if you put the next slide with the TNOs by the colors, because you have huge error bars, and usually these are cliff type objects. Yes. So the ones that are extremely red, the slope is beyond 40 yes. in the visible range usually. So why you have such a slow J minus R slope here? I miss a unit or no, maybe not.
Do you mean why these
Yes,
values are not
I would
reported?
expect higher values or
Because they're not calculated in the same way as the visible spectral slope at 0.55 microns. They're calculated.
you normalize in R
yes,
maybe?
and I'm normalizing at R. So
Okay.
this is why it's not the same values, but they're representing roughly the same thing. Although for the DiSCo observations, we don't go as low as 0.55 micron, for example. So,
Okay.
um,
And if you go to slide 27, so you say that there is a match between the CO2 irradiation and the methanol irradiation with the cliff and the double dip. There is still a shift, so they are similar but not exactly the same. Have you idea of why the band position is shifted over shorter or longer wavelengths for the tubes?
So for the double dips here and this little discrepancy between the CO2 irradiation, it's mostly due to how I extract the peak position, which is through a simple Gaussian fitting of the vibration band. And in the case of our CO2 irradiation here, the feature is quite symmetric because the ice is not as thick. But for the case of the double dips, especially for these ones that are the richest in CO2, the band starts to become asymmetric. And so this slight shift is induced by the fact that I'm only fitting one Gaussian, and so it's shifting slightly. But roughly, it's the same position. And for the clips, especially these ones, are shifted to much higher wave number compared to the methanol experiments. And for these, it's not due to the asymmetry of the band because the band is much weaker and so can really be nicely represented by a single Gaussian. So this is not the reason for the shift compared to the experiments, but it might be related to maybe uncertainty due to the noise in this region or to the sampling of the wavelength of the different wavelength points. Especially in this region, it's quite undersampled. So maybe observations at higher spectral resolution could help us see whether these objects are really shifted to higher wavelength range and why they're shifted.
And I have also curiosity about the thickness of ice. From the DiSCo program, have you been able to determine the thickness of different ice? Have you an idea? Or?
So for this, we would need some efficient spectral modeling. This is still very hard to do. And as of today, it's still impossible to fully model a spectra from the DiSCo dataset. But in this paper, Mario did fit just the CO2 absorption. But it's not really, it was not about to determine the thickness of the ice layer, but it was more so to explain the shape of the band. But for example, here, this CO2 ice being really fine grain, it really only represents a thin layer on the surface. But ideally, we should be able to fit the whole spectra and get an idea of whether it's layered or it's aerial, different patches of ices. But this, for now, is only possible for like separate portions of the spectra. So, for example, only trying to fit this region here. So also might be an indication that there are layers to the surface. So it's still a big open question.
Okay. And always about albedo and I over F, eyes are very bright. And from the Herschel program, we determine an albedo of 11%. I think also the brightest, except the dwarf planet and the Haumea family, has an albedo that is lower than 20%. So how you can combine this with the presence of ice? How plays the dark terrain? What is made of, and how is mixed with the ice eventually?
Yeah.
Have you any?
We were kind of surprised when we saw that all the clear water ice features were for the darkest objects, and really indicating that water ice might actually, even though we see its features, it might not be the dominant component, and there must be a big part that we're not seeing with the infrared observations that are dust silicates that are lowering this albedo. So again, with a full modeling of the ball-type spectra or laboratory works of mixtures of water ice grains with dust analogs, we could get an idea of how water poor the ball types actually are. And really, the brightest objects are the ones that don't have clear evidence of water ice. So they're not bright because of the water ice, but other ices.
Mm-hmm. Can I have a last one?
A last one.
So I look at the Trojan spectra that were published by other authors. I don't know if you have in the cup or somewhere, because there is we believe that it comes from trans-Neptunians, and there is no hints of ices except in one object that is Eurybate, I think, for the CO2 bands. So do you have any idea on what is the possible dynamical family source of Jupiter Trojans, and how surface may evolve from the Kuiper belt to the Jupiter region?
Yeah, this is a very nice question. I wish I had the answer, but
me too.
Maybe if we start with the Neptune Trojans, so closer to the TNOs, we can start to recognize some TNO-types, especially with all these ones being close to ball types. This one may be a double deep, which lost its CO2, kind of similar to Julia. And this one being more clearly a cliff with the very strong CH absorption here and the band here. So for the Trojans, for the Neptune Trojans, it's very clear that they come from the same population as the TNOs. They do have some differences which highlight that they're closer and so hotter than the TNOs. But for the Jupiter Trojans, it's impossible to make a straight comparison between the two because the ice component is almost completely gone.
But you agree that water, in principle, at 5 IU, you should find it.
Yes.
So where is it? This was my question. You should.
Yeah, but on this, it might be the organics that might help us to make a link between the TNOs and the Trojans, but it's definitely not the water ice. And especially here for this object that has some volatile, so the CO2, they think that this is that Eurybat is mostly like a collisional fragment, and so that this CO2 would be exposed, recently exposed due to this collision, but it might not be linked to the CO2 that we see in these TNO and Jupiter Trojan, Neptune Trojan surface types. So it's really difficult to try and make a link with the TNOs and the Jupiter Trojans. You might have to look at the refractories and not at the ices to make a link.
I'll stop here. Thank you again, and congratulations.
Thank you.
Thank you. Will, can you hear me?
Yes.
So you have the floor.
Okay, so I'll echo everyone. Congratulations, Elsa, on a really nice piece of work. And it's especially challenging when you're part of a large team and there's contributions from lots of people and you're trying to make a thesis that's just your story. And you did a really nice job of that. And this is very much in my mind because my student is defending in a month, and she is facing the exact same problem. And it's a lot of work to pick out a coherent story like you did. And my main question was going to be on the retention lines from Mike Brown's paper. Sergio beat me to it. So I will just say that I thought your answer was really good. And I basically, the punchline is that those retention lines are totally wrong. And, for the small bodies. And, which unfortunately messes up your story a little bit because really there is no methanol retention line out in the far outer solar system. So it's a little more complicated than this, but that's okay. It's in the literature. Somebody needs to do a better job, like you said. So let's move on to a question that hasn't been asked. So all of the laboratory stuff that you did, which was really nice work, you picture it applying to the surfaces of TNOs. However, before those TNOs formed, dust grains with more or less the same composition were in the nebula, and their cross-section to radiation, because they're all spread out, so they have a lot more surface area, is huge. And there's supernova going off in the early, lots of radiation. So could you comment on how much radiation the particles that go into the TNOs would have received even before they became TNOs?
Yeah, this is a nice question. I guess when we think about the primordial or an early composition of TNOs, we're thinking about matter that actually has already been processed in some way. And so, as you said, has undergone all these events, but were then incorporated within the TNOs, and this is our time zero for this matter. So the irradiation events I'm referring to are all after these events, and not addressing what happened before. But indeed, it should be nice to try and understand how this impacted the real original composition of these TNOs. But my experiments cannot really help in address this point. So maybe further information about the ice and the dust component in the disks could help to get closer to this real primordial composition of our planetesimals.
Thank you. You also talked in the thesis about, you lamented about the limitations of the DiSCo sample, which is a fair point. And you talked about now we could use what we've learned from the DiSCo sample to push to smaller sizes using colors. And I wonder if you have a favorite minimal filter set that would make a good sample for observing smaller objects.
This is a very, very nice question. So I'm just going back to some slides where I can show you these regions. We have seen that when we look at just the spectral slope in the visible, it's not enough to fully and ambiguously attribute a spectral and compositional group to one TNO, because there's overlap specifically between the double dips and some ball types and some cliff types. So it's not enough to look at just the visible spectral slope here. But using this spectral slope plus an infrared slope, typically this slope for balls here, for example, here where you don't have a band absorption is all red, whereas for the double dips, here it's red, but here it's more neutral. And for the cliffs, the near infrared slope becomes almost blue. So this might be a first indicator. And then we could also use the drop in reflectance at 3.5 micron, where for the bold type, the reflectance level is very high. For the double deep, it's intermediate, and then for the cliffs, it's really low. So at least these three could be able to nicely disentangle between the main compositional groups.
Okay, thank you. And then I think my last question is in the thesis in figure 3.8, so that's on page 87.
Thank you.
If you have that handy. I probably just missed something, but why does the ratio change very quickly at when the ice is very thin before it reaches a steady state? What's going on there?
Yeah, this is a nice point. So this is kind of our initialization sequence within this experiment. So these experiments begin by depositing a thin ice where the first ions that will encounter this ice. And then we trigger the rest of the deposition, which occurs within the irradiation. So probably the very first 100 nanometer of this ice has a very different dose from the rest, the thickness of the ice. And this is why we see this strong variation, which is really the initialization that will then be concealed by the whole thickness of the ice, which is at a steady irradiation dose.
Okay, that makes sense. Thanks. And I don't have any other questions. Nice work.
Thank you.
Thank you very much. So, want to say the word now? Yeah, sorry. No, Noemi.
Well, I mean, we speak frequently, so I'm not sure if I have many questions and way less if they're smart, but I'm curious about one next step that is what you mentioned, modeling, trying to model this spectra, and the possibility of modeling the complex organic matter, of having good reflectances and way more optical constants to try to reproduce the slopes and the change in the slope and also the aliphatic path. We have been traditionally using optical constants from Titan tholins and Triton tholins that are not optimal for this. So they don't really help now. They help for specific areas, but not for all of that. So my question for you as an laboratory person is, now that from the spectrum, we know a little bit more what is on the surface of these guys. Could you imagine, or which would be the direction that we have to follow to create tholins that are good for TNO surfaces?
This is a nice point. So there's the idea of really looking at just the organic matter part on its own and well characterizing their optical constants and using this in the models that try to represent all the features on the TNO spectra. But you could also look at these organics within the irradiated ices. And this is what is kind of available with the data from my experiments, is that we could try to recover the optical constants from the irradiated ices to really already mimic all the complexity that we expect to happen on TNO surfaces. And it would be interesting to see if this gets a good match in terms of the color and the CH absorption band ratio, to see how this would improve. So specifically for the cliff type, but yeah, it would be different for each of these types.
Yeah. So if I tell you, cook for me a good DiSCo-tholin, it would be the ingredients. Like maybe one for the double dip, one for the cliff.
Yeah. So for the cliff, I think we have to start with methanol, but I explored also methanol mixed with water ice. And we do think that there might have been some initial water ice within these cliffs, because both in terms of the slope And in terms of the CO2 ratio, the mixtures of methanol and water ice match better than pure methanol initially. But it also might be interesting to look at ices that initially contain CO2 alongside with the methanol and see how this changes. So it's really about mixing the carbon to oxygen to hydrogen ratio. And then specifically for the double dips, one thing that is kind of that I did not really touch upon, but it's that the CO2 ice seems to be mostly pure on these surfaces, but we have a super strong OH feature, and the CO2 is not mixed with this OH feature. So this suggests some sort of segregation, of separation between these two phases. Is it aerial or is it layers? I'm kind of tempting to say more layers, since the objects that go further in, the double dip types that would go further in, lose this CO2, but will keep the OH feature. So yeah, lots of things to see still from this. Thank you.
Thank you very much. Want to tell a word before I ask my question and then yeah. So thank you again also Elsa. Je vais parler en français, histoire que on sache que quand même quelqu'un.
Et des soulagements.
Voilà, exactement. Je vais redire un certain nombre de choses. La première chose, c'est que la lecture de votre thèse était très agréable et très agaçante à la fois parce que vous avez l'art du teasing, parce qu'au bout de 80 pages, j'avais pas encore commencé dans le dur du sujet. Donc, mais c'est remarquable parce que vous avez fait un état de l'art qui, comme l'a dit ma collègue, sera, je pense, utilisé par d'autres choses. Donc ça, c'était vraiment agréable. Pour ce qui est des questions scientifiques, bon, vous avez entendu, Sergio Iopolo n'était pas d'accord, aux USA on n'était pas d'accord, et j'étais pas d'accord non plus, donc je vais pas insister sur ce passage-là, mais il était dans le teaser, donc là j'étais un peu, je me disais chouette, on va pouvoir discuter. Alors je vais pas discuter de ça non plus avec vous. J'aurais plutôt envie de discuter sur la première chose, c'est sur les équilibres chimiques. Donc je vais vous poser une question simple. Si vous aviez fait un mélange d'eau et de CO à assez basse température et que vous aviez tiré dessus avec vos protons, est-ce que vous ne pensez pas que vous auriez obtenu du méthanol et un équilibre CO-CO2 similaire?
Oui, du coup, il y a pas mal d'expériences qui ont été faites dans cet esprit-là, où souvent ce mélange de eau et CO, ça va former du CO2 parce qu'on est dans un milieu assez oxydant où on peut former beaucoup de CO2. Et on peut aussi former du méthanol par la contribution des deux hydrogènes sur le carbone. Mais ça ne va pas suffire pour expliquer une quantité de méthanol assez importante qui est nécessaire pour avoir, par exemple, tous ces CH alipatiques et une pente rouge, par exemple. On va quand même rester en commençant avec de l'eau et du CO, on reste dans un milieu très oxydant où il va manquer beaucoup d'hydrogène pour tomber sur des surfaces qui ressemblent à des cliffs. On va peut-être plutôt se rapprocher des surfaces comme des bowls, surtout si l'eau est largement majoritaire. Dans mon scénario d'irradiation, pour expliquer la présence du CO sur les double dips et sur les cliffs, c'est aussi cohérent avec une irradiation sur les bowls. En fait, on est dans un milieu tellement oxydant qu'on va favoriser beaucoup plus le CO2 par rapport au CO et que peut-être on peut former un petit peu de CO, mais on ne le verra pas.
Mais alors, je ne sais peut-être pas lire vos graphes, mais vous montrez celui où il y a plein d'eau partout et pas beaucoup de CO2 en me disant c'est celui-là qui est le plus oxydé. Alors, en tout cas, je vais poser ma question autrement, vous inquiétez pas. Là, je suis en train de vous emmêler. C'était pas ça le but du jeu. Je la pose de façon plus favorable, mais c'est la même idée. Est-ce que par le fait que vous ayez tendance à vouloir dire je pars d'une composition trop abondante au méthanol par rapport à des conditions initiales qui seraient celles du milieu interstellaire, parce que dans le milieu interstellaire, on part avec 5% de méthanol. Est-ce que, du coup, avoir un peu de CO et un peu d'eau, ça permettrait pas, avec de l'irradiation, d'arriver au même résultat.
En plus du méthanol.
Eh bien oui.
Oui, complètement. Ça, ce serait, oui. Donc, ce serait dans l'idée aussi de investiguer toutes les configurations initiales possibles avec du méthanol qui donneraient au même résultat et montrer à quel point ça peut être dégénéré. Et OK, on peut dire qu'il y avait du méthanol à la base, mais peut-être on ne pourra pas dire exactement combien et surtout la contribution de ces autres molécules-là. Après aussi, quand on part avec du méthanol pur et qu'on l'irradie, on va former de l'eau, on va former du CO, on va former du CO2. Et donc, à cette étape de temps d'irradiation 1, ça peut être considéré comme un mélange T0 pour de l'eau, du méthanol, du CO, du CO2, et qui va lui aussi après évoluer avec les doses d'irradiation suivantes et en fait retomber sur la même chose.
Mais, merci. Le deuxième point, à part les équipes chimiques, donc on a parlé des équipes chimiques, c'est les problèmes d'épaisseur qui sont en fait critiques à la fois dans vos expériences et dans vos observations. Parce que la question, c'est de savoir à quelle profondeur ça joue, à quelle épaisseur c'est important. Et vous l'avez très bien montré à la fin sur la pénétration des ions énergétiques versus l'infrarouge que la physique est probablement dans le fait que vous sondez des profondeurs égales. Je ne vais pas entrer dans les détails, mais je me demande si les pentes rouges sont pas liées à ces problèmes d'épaisseur optique. Mais je suis pas assez expert pour vous poser la question comme ça. Par contre, j'aurais tendance à vous poser une question. Je suis absolument d'accord sur toutes vos observations astrophysiques et expérimentales, et même la façon dont vous tirez des conclusions. Par contre, pour fabriquer une histoire au sens scénario d'évolution des choses, comment est-ce qu'on fait pour passer de 40 nanomètres, 50 nanomètres ou 100 nanomètres avec une composition de glace du milieu interstellaire à votre film actif dans l'infrarouge 2 micromètres sur un gros machin de 2 km, 2000 km, pardon, à 50 années AU de nous. Donc, comment est-ce que si vous aviez fait l'expérience, comment vous faites pour passer de ces toutes petites épaisseurs où on contrôle plutôt bien l'optique à ce que vous observez, où on contrôle aussi tout bien l'optique, mais entre les deux, c'est tout votre scénario d'histoire.
Oui, ça a été un peu le challenge de ces manips. Ça a été de sortir de ce qui est relativement bien connu pour les glaces interstellaires, où c'est à des températures assez basses, des glaces très fines, où on a des belles bandes infrarouges, et de se rapprocher le plus possible, surtout pour trouver une réflectance diffuse des surfaces des objets trans-Neptuniens. Où là, donc, j'ai voulu essayer les glaces les plus épaisses possibles, tout en ayant la contrainte que plus je fais une glace épaisse, quand j'irradie en même temps, plus la dose va être faible, donc il faut en même temps irradier très longtemps. Et donc, oui, c'était de jouer avec ces contraintes pour avoir la glace la plus épaisse possible, irradier le plus possible pour reproduire les doses qu'on pense s'être accumulées sur ces surfaces-là. Et encore là, cette irradiation, ces manips-là, ça reproduit que ce qui se passe sur les surfaces des planétésimaux depuis leur formation, mais ça ne prend pas en compte tout ce qui s'est passé avant.
Ok. Merci pour ces réponses. Je vais laisser la parole maintenant aux encadrants pour nous dire, non pas des questions, mais éventuellement un éclairage sur ce travail.
Bien. S'il vous plaît. Okay, I will do it in English and I will translate in French. Je vais traduire en français, comme ça tout le monde comprendra. Okay, so first of all, thank you, Elsa, because you are giving me the opportunity to brag and say, I always knew. I had like a feeling during the first discussion we had in my office 6-7 years ago. And then I was absolutely sure a few days into your undergraduate internship, I was sure that you would be brilliant and perfect for research and astrochemistry. Merci de me donner l'opportunité
de me vanter et de dire j'ai toujours su. Je le savais depuis le début, depuis même la première fois où on s'est vu, tu es venu dans mon bureau pour discuter stage. Et puis ensuite, vraiment pendant le stage, enfin les premiers jours du stage, j'étais certaine que tu avais toutes les qualités nécessaires, non seulement pour faire de la recherche, mais en astrochimie, c'est-à-dire en fait à l'interface physique, chimie et astro. Well, let's be honest, I'm pretty sure all your teachers at that time had the same feeling like me. And by the way, thank you to them for sending you to me. Je suis absolument certaine que tes profs à l'époque du magistère avaient la même sensation et que c'est la raison pour laquelle ils t'ont dirigé, orienté ici vers l'IAS, vers moi. Et donc, merci à eux, vraiment. Yeah, but let's be serious. So being, let's say, brilliant, having the perfect skills and the perfect mindset for scientific research, it's not enough to accomplish what you did. You, first of all, you seized all the opportunities that we offered you, and this is a quality. And then you worked really hard, and you have adapted to the several heavy constraints you were dealt with during your PhD. And I'm including in there the fact, dealing with 3 supervisors with the 3 different ways of thinking. But you held on and you kept moving forward. And this is certainly the reason why I'm not only proud of you, but I'm really looking forward to your next steps, your next chapters. Je vais traduire. Ça suffit pas en fait d'avoir des compétences académiques, d'être voilà, particulièrement fort scientifiquement ou d'avoir l'état d'esprit qu'il faut pour faire de la recherche scientifique. Ça, c'est nécessaire, mais c'est pas ça en fait qui suffit pour rendre compte et pour permettre de faire tout ce que tu as fait en à peine un peu plus de 3 ans, enfin 3 ans en fait. D'abord, il a fallu savoir ce que tu as fait en fait, saisir vraiment la chance qui t'était donnée de faire cette thèse, de rejoindre le groupe DiSCo, voilà, tout ça. Énormément travaillé. Et puis aussi, tu t'es beaucoup adapté à plein de contraintes compliquées, fortes, que tu as rencontrées sur ces 3 années. Et j'incluais là-dedans le fait de devoir avoir 3 encadrants avec 3 manières différentes de penser, de faire les choses. Ça aussi, c'est pas si simple. Mais ça aide pour l'avenir, hein, parce que tu vas avoir à travailler avec plein de gens différents. Et ce qui est bien là-dedans, c'est que voilà, tu as tenu bon, tu as continué, tu as avancé, et ça donne ça. Et c'est la raison pour laquelle non seulement je suis fière, mais j'ai hâte en fait de voir la suite, de voir ce que tu vas faire dans les années à venir. And I will conclude by saying that to be a good scientist, you never stop growing, you never stop learning, you never stop improving. It's more or less our job in a way, I would say, basically. And we are lucky for that. And we are lucky for having you soon as a peer. I know. Donc, pour moi, enfin, être un bon scientifique, c'est quelqu'un qui n'arrête jamais en fait de s'améliorer, d'apprendre. C'est ça. C'est un processus qui s'arrête jamais quand on est vraiment fait pour ça, fait pour être un bon scientifique, une bonne chercheuse. Et c'est aussi ça, la raison pour laquelle j'attends la suite impatiemment et je suis très contente que un jour, je pourrais t'appeler ma collègue, en fait. Voilà.
Oui. Je vais faire en français. Merci pour ces 3 années, Elsa. Ça a été un vrai plaisir de travailler avec toi. J'ai beaucoup apprécié ta rigueur, ta personnalité aussi, très agréable à vivre. Et je n'ai aucun doute que tu feras une excellente chercheuse, comme l'a dit Damien. Et merci aussi pour ta présentation qui était hyper claire, hyper didactique. Voilà, quoi. Ça m'a pas étonnée. Enfin, je veux dire, je savais que ça allait se passer comme ça. Donc, en tout cas, tout ce que je peux te dire, c'est bon courage pour la suite. Et je suis sûre que tu vas t'éclater à Grenoble et que ils ont de la chance de t'avoir en postdoc. Et voilà, je m'arrête là. Merci pour tout.
Thank you. There are a few things I would like to say to the colleagues. First of all, thank you all for accepting to be part of this committee. And it's as you saw, it is a beautiful work, but there's much more than she couldn't actually put in the manuscript. This project began with some ideas in mind, and then it evolved during the first discoveries of DiSCo, and the spectra were arriving, and with Noemi we were discovering things, and everything was going so fast. And also your PhD subject evolved during the thesis, and so many experiments that you did at the beginning are not included in the manuscript because they were maybe not relevant anymore, or just there's no time to do everything. So also this is to clarify a few points with my colleagues here. In particular, lots of experimental work with mixing ices with silicates, with trying different analysis on the residues, and many other things that are in fact very interesting. And maybe hopefully someday you will publish. So at some point. So a couple of things I would like to say. First is, it is true that what Donia said, that she came to my office once and she said, I think I found a good student. Which means a lot, if you know her. So, but it took me quite a while to understand really what she meant. And being your supervisor has been also an interesting exercise for me. Very frustrating at some point. Can you imagine like the poor supervisor that enters the office of the student and say, hey, wait, I have a great idea. We should try this, really. And the student looks at you and says, yeah, I tried already. It doesn't work. And this happened a lot of times. So at some point I realized that my job would be a job of silence and saying less than I would normally, and so a different kind of supervising, which is very for me it's been a very intense and great experience, really. So thank you for that. And last thing is also thank to Noemi. At some point at the beginning, we said, okay, we should work on the CO2. And Noemi was organizing lots of course, and we should publish the papers. And it's a stressful situation, things and so on. And so I said, okay, let's see if Mario and Elsa can work together on the CO2 paper. And I mean, I think this was crazy, right? I mean, we put you guys in, and you managed, and you two managed to work together. You never met before. It's magic, really. It's something that, so it could have been terrible, and it turned out to be beautiful. And yes, and this will remain. So congratulations also for that, for joining the different groups. Et aussi un grand merci, je pense, de la part de tous les collègues du laboratoire qui ont eu la chance de t'avoir à leur côté pendant toutes ces années. Voilà, je pense que c'est manqué.
Bien, merci beaucoup. Nous, on va se retirer à côté pour délibérer. Ça va être long et difficile, mais...
Okay, so we're going to switch to the other Zoom room.
Je peux réactiver. C'est bon, j'ai réactivé mon son. Non, non, on l'a réactivé. Il faut juste le temps qu'on vérifie que ça. C'est bon, super. C'est bon.
Bon, alors Elsa, donc je vais faire l'annonce en français, même si mes notes sont en anglais. Donc le jury a délibéré et a trouvé que d'abord la présentation était vraiment très claire, très pédagogique, très agréable à suivre, avec une utilisation très astucieuse des graphiques et des figures qui nous permettaient vraiment de suivre le travail. Comme ça a déjà été souligné dans les questions, c'est outstanding en anglais, et on a trouvé assez remarquable la cohérence globale du travail, alors qu'on sait que le travail a été constitué en marchant, et arriver à un résultat aussi globalement cohérent et vraiment remarquable. Après, passons à la partie des questions et des réponses. Tu as répondu de façon excellente aux questions. J'ai même dit agaçante parce que tu as anticipé les questions sur des slides que tu avais préparés. Sans doute, voilà, c'était vraiment remarquable de ce point de vue-là. On est tous unanimement convaincus que tu es déjà une excellente chercheuse. Et donc, il reste encore quelques étapes avant de décerner le titre de docteur. Une très technique, il faudra déposer le manuscrit au bon endroit en ligne. Une deuxième étape qui est plus solennelle, ça va être de prêter serment. Donc, je pense que tu as prévu ça. Alors, pour expliquer un petit peu en quoi consiste ce prêter serment, donc je donne le contexte à ceux qui sont peut-être un peu en dehors du champ de la discipline scientifique, mais vous avez entendu que les scientifiques n'étaient pas d'accord avec tout, et que il y a des choses pour lesquelles le jury n'était pas complètement d'accord, et même pas du tout d'accord, on peut le dire, sur certains aspects du travail, qui d'ailleurs pas ton travail, mais le travail d'autres. Mais ça fait partie de la discussion scientifique et ça fait partie des choses. Et ce serment, le diplôme de docteur est un diplôme, mais c'est aussi un titre. Ça veut dire que c'est le plus grand titre que peut donner l'Université de Paris-Saclay. Et d'une certaine façon, ça fait rentrer dans la communauté des scientifiques. Alors, à titre personnel, je t'offre ce livre qui est Micro-Mégas de Voltaire. Et alors, ça, c'est pas trans-Neptunien parce qu'on n'avait pas encore découvert Neptune, mais l'un des héros vient de Sirius, qui est clairement trans-Neptunien. Et ce livre, alors je vais faire quelque chose qu'il ne faut pas faire, mais à la dernière page, le héros offre un livre aux hommes. Et le scientifique ouvre ce livre, et dans ce livre est censé contenir toute la vérité. Donc le scientifique est ravi, il rentre à l'académicien, il ouvre le livre, et le livre est blanc. Et ça, en fait, c'est le livre blanc de la recherche. C'est que, en fait, c'est à nous, et donc à toi maintenant, les chercheurs ou les scientifiques, de continuer à réécrire ce qui doit être écrit. Et en fait, c'est un devoir, comme on l'a dit, et c'est un droit de pouvoir faire vivre cet esprit de critique et de discussion jusqu'à ce que finalement on se mette d'accord. Mais sans esprit critique, sans discussion et sans le droit de se tromper et de réécrire la science, eh ben on serait pas scientifique. Donc maintenant que j'ai donné des explications de background, je te laisse prêter de serment pour devenir docteur en sciences de l'Université Paris-Saclay.
Merci. En présence de mes pairs, parvenu à l'issue de mon doctorat en astronomie et astrophysique, et ayant ainsi pratiqué, dans ma quête du savoir, l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats.
Félicitations.
Merci. Et là, c'est le moment où moi j'enchaîne. Bon, je pensais pas déjà verser ma petite larme dès maintenant, mais je vais peut-être faire en anglais d'abord pour les membres du jury et tous mes collaborateurs internationaux. Many thanks to the members of my jury for first agreeing to review my work and then for providing me with very valuable insights and questions and discussions. I was very happy to get to discuss with you all, especially considering that when I first began my thesis, I was kind of intimidated by many of you. So it's very nice now to be able to discuss with you kind of as equals. So I'm very thankful for the discussions that we've had and your outlook on my work. Many thanks to the members of the jury. Then I would like to thank the DiSCo team, starting of course with Noemi. I'm so happy that she welcomed me into this group, that she allowed me to take this opportunity and really made me give the best of myself and really providing for a nice environment where we could all collaborate and learn from each other. So I'm very happy that I could seize this opportunity, that you gave this opportunity to me, and that, well, you calculated, but for the past 2 years, 2 months and 36 days since we've had the first observations, it's very nice to see where we've come. I'm very happy to be the first DiSCo-TNO Ph.D. student, but there will be 2 more to come, so look out for the thesis of Brittany and Lucas. And then within all the members of the DiSCo team, some of whom may be online. So hi if you're listening. I want to thank especially Mario for his trust and his advice. It was very nice working with you. I want to thank Carol and Brittany for their friendship. It was very nice to have them here for a few weeks in this lab. I want to thank Nuno for his funny, witty, philosophical insights. I want to thank Yvonne, Josh, and Lucas for their continuous encouragement. It meant a lot. I want to thank Thomas, Aurélie, Brian for their help, which was very invaluable. Just a huge thank to the team for welcoming me, for your trust, your support, and your openness. So maybe now I will stop with the English and switch back to French. Après, je vais évidemment remercier mes encadrants, donc mon trio d'encadrants, pour toute leur sagesse, leur perspective, toutes les différentes opinions qu'ils m'ont transmises, et d'accepter aussi que je choisisse, on va dire, quelles opinions je prends en compte, lesquelles je construis pour vraiment pouvoir avancer. Donc, merci beaucoup pour tous les aspects complémentaires que vous avez apportés. Merci spécifiquement à Zaya pour son accompagnement très consciencieux. Merci à Donia, vraiment pour ce qu'elle a dit, d'avoir vu son potentiel, mon potentiel très tôt, on va dire, quand je suis arrivée en cherchant un stage de L3 à l'automne 2018 pour commencer en juin 2019. Donc ça commence à faire longtemps. Merci à Rosario pour toute la confiance qu'il m'a accordée, même si parfois j'ai trouvé que c'était peut-être un peu trop, mais en fait je suis contente de voir ce que ça a donné. Je suis contente de cette indépendance parce que je pense qu'au fond c'est ce que j'aime, et du coup je pense que j'ai vraiment pu grandir pendant ces 3 ans, et c'est vraiment très très grande partie grâce à toi. Donc merci beaucoup à tous pour tout cet accompagnement, cette guidance, voilà. Et après, au-delà des encadrants, il y avait toute l'équipe astrochimie qui était vraiment une super ambiance, un super groupe pour me permettre de faire ce que j'ai fait. Donc je pense surtout à Obadias qui m'a été le soutien technique de presque toutes mes manips. Et donc merci à lui pour tous les nombreux tanks d'azote, pour les nombreuses bouteilles d'hydrogène et d'autres choses que j'oublie. Et les boulons. Oui, pour les boulons. Et merci au reste des membres de l'équipe astrochimie. Alors, on est une petite équipe, donc il n'y en a pas non plus énormément. Mais surtout, merci à Zélia, qui a été vraiment mon oreille attentive et affectueuse, et toujours sa porte de bureau ouverte. Et pardon, faut pas te regarder. Et Zélia, pour moi, c'est ma grande sœur dans la recherche, et je serais très contente de la savoir dans la communauté, dans la recherche, de pouvoir la recroiser en conférence et compagnie. Donc voilà. Merci Zélia. Après, merci à l'équipe de Sidonie, qui m'a permis de réaliser toutes ces expériences d'irradiation. Donc spécifiquement, merci à Philippe qui est là avec nous, qui a très gentiment accepté quand je lui demandais est-ce qu'on peut faire des irradiations de 6 heures et c'était pas très pratique, mais il a toujours dit oui, il a toujours été très volontaire, il m'a toujours aidé, il a toujours fait de son mieux, et tout ça, ça aurait pas été toute ma thèse, ça aurait pas été possible sans lui, donc je lui dis vraiment un grand merci. Et côté irradiation, j'ai fait des choses dont j'ai pas du tout parlé ici, qui sont des séances d'irradiation au Ganil avec le dispositif Ilias, où donc j'ai toute l'équipe qui m'a accueilli pour un week-end de Pâques qu'on a passé au milieu des pompes et des accélérateurs, c'était bien sympa. Donc si jamais ils sont en train d'écouter, je les remercie aussi pour pour tout. Après, je voulais remercier l'école doctorale, donc le D127, qui s'occupe vraiment très bien de ses doctorants, et spécifiquement à Thierry Fouché pour son enthousiasme et ses encouragements vraiment continuels. Ça m'a vraiment beaucoup touchée. C'était, je pense, très important pas que pour moi, mais pour tous les doctorants. Enfin, c'est vraiment, on se sent soutenu dans tout le travail que vous avez fait, donc merci. Après, les membres de mon comité de suivi. Donc, quand on fait une thèse, on a des membres extérieurs qui nous suivent un peu de loin, juste pour voir comment ça va. Et donc, moi, j'avais 2 Émilie, une au labo et une hors du labo, qui s'occupaient de moi et qui sont peut-être à distance. Et donc, je les remercie aussi pour leur écoute. Et après, il y a en dehors de la recherche, j'ai enseigné pendant 2 ans au département de chimie à l'université Paris-Saclay. Et donc, je voulais remercier les responsables des UE où j'ai enseigné, spécifiquement Valéria, qui est passée, mais qui a dû partir, je pense, qui était d'ailleurs ma référente de stage de L3, donc encore une que je connais depuis quelques temps. Et pour rester dans l'enseignement, je voudrais remercier mes professeurs du magistère, qui m'ont donc bien aiguillée vers Donia, comme elle a dit, et notamment Anne Lafosse, qui est peut-être en ligne, qui était ma professeure de spectroscopie, donc quelque chose qui m'a été très utile, comme vous avez pu voir dans ma thèse. Et après, au niveau des professeurs, on va retourner encore plus loin, on va aller au lycée, où j'ai invité, et j'ai la chance qu'elle soit présente, 2 professeurs de lycée, Madame Parou, ma professeure de physique-chimie pendant les 3 années du lycée, et Madame Le Gouen, ma professeure de sciences et vie de la Terre. Juste merci d'être là, d'avoir accepté cette invitation alors qu'on ne s'est pas vu depuis bientôt 9 ans. C'est vraiment super de votre part d'être venu. Et moi, je voulais prendre cette opportunité pour vous dire merci de m'avoir donné l'amour des sciences naturelles, et de m'avoir donné les bases pour faire ce que j'ai fait aujourd'hui. Et j'ai un petit mot que Madame Le Guen, qui était ma prof principale en terminale, m'a écrit le 30 mai 2016. Elle m'avait dit « Bravo et merci pour cette fin de scolarité exemplaire. Ton courage et ta ténacité sont de bon augure pour la poursuite de tes études. » Et je pense qu'elle a eu raison. Donc, voilà, merci beaucoup d'être là et merci aux enseignants qui travaillent et qui parfois ont l'impression que c'est très ingrat, de dire que quand même ça vaut le coup. Après, je vais passer à mes amis. Et donc là, on va faire par ordre chronologique avec les amis de prépa. Donc Claire, Alexis et Géraud qui sont assis là au premier rang. Merci beaucoup d'être venus. Merci d'être toujours là, malgré le fait que la prépa, c'était une époque parfois un peu tumultueuse. Mais on dit que les amis qu'on fait en prépa, c'est les amis qu'on garde toujours. Donc je pense que c'est assez vrai. Et j'ai une petite pensée aussi pour Clément et Ségolène qui ne sont pas là, mais qui sont peut-être en ligne. Et après la prépa, il y a eu le magistère, où j'ai là Anaïs, Théo et Raphaël qui sont là avec nous. Il y aurait aussi Aristide qui est peut-être sur le live. Et merci à eux pour tous les moments, tout ce qu'on a partagé dans la fac, bâtiment 470, dans la salle C17. C'était une super salle où on a commencé toutes les parties de tarot dès qu'on avait 15 minutes de pause. C'est une addiction qui continue ici au labo. On joue beaucoup au tarot. C'est le tripot du 3e étage. Merci pour tous les moments qu'on a passés ensemble en cours, pour toutes les fois où on s'est serré les coudes pour travailler, réviser, faire les TP, tout ce que font les étudiants, quoi. Et donc je suis ravie d'être toujours amie avec vous maintenant et que ça continue très longtemps. Et maintenant, les amis de maintenant, on va dire que c'est tous les précaires du laboratoire qui vont se reconnaître. Donc il y a des nouveaux, il y a des anciens. Il y en a, j'ai trop peur d'oublier des gens, du coup je vais pas dire tous les noms, mais notamment Valentin qui m'a sauvé une pompe. Merci beaucoup. Je pense aussi surtout aux absents, Stéphano, Tania, Max et Marion, qui, je pense que certains sont en ligne. Merci d'être tout ce que vous avez apporté à l'équipe, à la vie du laboratoire, créer une super ambiance pour tout le monde. D'être aussi des bons grands frères de recherche, le genre de personnes qu'on a vraiment hâte de revoir en conférence. Et c'est pour ça que c'est trop bien les conférences de pouvoir se revoir. Donc oui, merci à tous les précaires du labo. Et avec une mention spéciale aux membres du bureau 311, qui est donc le bureau que j'ai partagé pendant les 2 premières années avec les 2 Yann, donc Yann Eto et Yann Ibar. Et ensemble, donc, on constituait le bureau Pastèque, qui a été donc une grande partie de ces années de thèse. Donc merci pour votre soutien, pour tous les moments rigolos qu'on a eu ensemble, pour toutes nos discussions politiques. Et c'est génial que ça continue parce que voilà, le bureau Pastèque, c'est pour toujours. Donc, Et ensuite, il y a eu, évidemment, vous êtes partis, vous avez soutenu, j'ai versé ma petite larme à vos soutenances, mais vous êtes là pour la mienne. Et maintenant, dans le bureau, il y a Laura et Rachel. Et merci beaucoup à Laura pour tout, parce que t'es géniale, Laura. et... et voilà. Et après, tout ça, c'est aussi... si j'en suis arrivée là, c'est quand même grâce à ma famille et surtout à mes parents qui m'ont toujours soutenue dans mes choix d'études et de vie, même si ça pouvait paraître des choix un peu pas confus, mais on va dire un peu abstraits. Et non, mais oui, pour m'avoir donné cette curiosité, cette envie d'indépendance aussi, cette perspective sur la vie qui me fait que j'aime les sciences fondamentales et oui, tout ce que vous m'avez apporté qui fait de moi la personne que je suis aujourd'hui. Et pour finir, Titre, qui est donc, si vous ne le connaissez pas, mon copain depuis longtemps. que mes professeurs de lycée connaissent parce qu'on s'est connus en seconde, parce qu'on était dans l'ordre de l'alphabet, nos noms se suivent et du coup on a été mis côte à côte le premier jour et c'est de là que tout est parti. Donc merci à l'alphabet. Merci à Titre pour toute la vie qu'on construit tous les deux, pour tout le soutien au quotidien et j'ai hâte de la vie qui nous reste à construire après. Et je pense que je vais m'arrêter là parce que ça fait déjà pas mal. Et maintenant, je vous invite à vous diriger vers le pot où nous allons pouvoir trinquer et manger et processer toutes les émotions. Merci beaucoup. Merci. Ben, super, merci beaucoup. J'aime beaucoup lire, donc c'est. Oui.
Elle est aussi littéraire, donc.
Ben voilà, c'était le grand choix, la science ou la littérature, et du coup, maintenant j'essaye de mélanger les deux un peu.